Okay, thank you for joining us this afternoon. So I'd like to start the KGRI, Keio Global Research Institute lecture series. Today, we invite the Professor Donald Keith Martin from the TMIC, IMAG, and Faculty of Pharmacy, University of Grenoble-Alpes in France. And actually, between Keio University and Grenoble, France, we were getting a very important strategic partner. And actually, 5 years ago, the Faculty of Science and Technology started the collaboration, and now we are expanding this collaboration to the medical field as well. And today, he's going to talk about building on biomimetics challenges for the symbiotic medical devices that are bio-inspired and nanostructured. So he's been working on the nanotechnology and produced a lot of very interesting medical devices as well. So we look forward to the further collaboration. And first of all, we'd like to learn from him this afternoon. Thank you.
Okay, so that works. Everyone can hear. Okay, good. So yeah, thank you, Masato, for the invitation, and it's a pleasure. I've had the opportunity twice in Grenoble. This is the first time in Japan, but 2017 was the first time we met, and it was an interesting. There's an interesting potential and perspective for collaborations with Grenoble and Keio University, which is really quite interesting. So I'd like to talk about bioinspiration and symbiotic medical devices. So my work I'm Australian, so I was doing a lot of work on ion channel, patch clamp electrophysiology, cell membrane transport, and now in Grenoble my lab is converting a lot of that basic scientific information to medical devices that are symbiotic. And I'll explain what I mean by symbiotic, but the point being that by starting out designing a medical device using biological components helps to get biocompatibility and helps to develop medical devices that can truly integrate and become symbiotic, which is the key point about symbiotic. So what I'd like to do, just 3 points. I want to talk about challenges for implantation. In fact, I could, if we could do this. So I want to talk about the challenges for implanting symbiotic medical devices, and just discuss a little bit what a symbiotic device is compared to what other devices that you would see, and this concept of duplex communication, because as I'm finding more and more, and as probably you're all seeing as well, that the concepts of medical devices really benefit by taking also the concepts of engineering and physics and chemistry. Perfect, thank you. Taking all those concepts, adding that to a medical context. So, duplex communication is something that the electrical engineers have been playing with for a long time. Two-way communication. A device that listens and a device that talks. So that's the concept of symbiotic. When you put that in the body, there's a communication. So I'll discuss a little bit about that. And then taking these concepts into how you go about designing devices and some examples of those devices, taking a bio-inspired approach, and hybrid devices. I want to discuss the concept of engineering, using the concepts of engineering, physics, chemistry, biology, and electrical engineering concepts, putting those into devices that contain biological components. And then kind of looking to the future. and this is where I'm particularly interested to discuss the concepts of brain-computer interface and the ideas of really pushing the boundaries of what one can do with medical devices that can truly interface with tissues and tissues of the body. So that's the direction of what I'd like to discuss. And in considering what are the challenges, it's always useful to see what existing medical devices look like. Are they symbiotic, and what's the duplex communication? So if we look at existing medical devices that are either, you can wear them on your wrist, internally implanted like pacemakers or pumps like this, external or internal, and hospital-based systems or systems of early warning. All of these kind of medical devices, they measure something and deliver something. Either deliver electrical signals to pace the heart, they pump drugs. It's very difficult to have closed-loop insulin-secreting systems, for example. It's very easy to have implanted pacemakers and devices that deliver electrical signals. Deliver. It's easy to take measurements, and even external pumps. I mean, these are programmed. So what I would suggest that these kind of medical devices do things being deliver energy or deliver materials one way, either programmed by human beings to deliver, not really listen and being symbiotic. That's the key point. So looking at those in detail, insulin pumps still, the patient has to take a fingerprint, they prick of blood to measure and program and make sure that the device is programming the correct delivery of insulin. Pacemakers, they're programmed to deliver pulses to stimulate, either defibrillate or pace the heart. Even MEMS in the retina, for example, they're sensing devices. These devices are useful, but not, to my mind, measuring and being truly symbiotic. The concept that I want to push the boundaries of are devices existing, medical devices. It doesn't matter too much if they're encapsulated, because you can have a medical device with like a pacemaker that will deliver a wire into the heart, deliver electrical systems in the heart. You want that pacemaking can to be encapsulated and to be a system that can live inside the body. You don't really care if materials, ions or chemicals come into the pacemaker. It depends on the intention. So a device like this, encapsulation is okay. If we want to have a device that relies upon taking chemicals from the body, transforming those chemicals into either power or some other system, so that this device then functions like an organ, then we do care about the membrane that needs to retain a permeability and a communication of materials and power with the body. Compared to the devices that I have examples of, we don't really care too much about whether there's a permeable membrane. So these are the concepts of a duplex device, a two-way communication in a device that's symbiotic, and it kind of pushes where we have to think about designing. So designing a device like this means that we have to consider the permeable membranes need to retain permeability. So we retain the same levels of water transport, ion transport that exist in organs of the body. And that's actually quite a difficult engineering concept and difficult engineering task to achieve. So that's the concept of a symbiotic implantable device, raising the issues of biocompatibility. So as an engineer these are the concepts trying to design biocompatible devices. How do we go about that? Interesting, because in 1970, 72 I think that is, or so, there's a lot of work done. Going back to history is an important thing to do because we learn from that not to make the same mistakes. The concepts of the challenges and limitations of biocompatibility were described as these. Lack of agreement candidate materials, specifications needed to be worried. All about materials, because the concept in 1970s was implanting a device to deliver power or deliver an osmotic pump, deliver drugs. And so the systematic approach was you have to match the engineering properties to the implant materials and the biological environment. Okay, so the issues about biocompatibility. And this is all coming to the concept of how we think about symbiotic devices. This is what the field is existing. So as an engineer trying to design biomimetic systems, one has to consider what the problems could be in designing devices that go in the body. So I'm leading up to the bioinspiration, the biomimetics. Okay, so if we come forward to now in 2012, biocompatibility, interpretation limitations, very similar to public thoughts 40 years ago. Not much has changed. Not much has changed because the scheme is looking very complex, much more complex than it was in 1970, because there's a lot more standardization in ISO standards, ASTM standards, a lot more standardization. So this is paperwork. But the overall principles are much the same. Where is the questions? Is the implanted device releasing any compounds? Is it toxic? Does the implant supply support differentiation of the desired cell type? Is the implant trying to support differentiation, etc.? These concepts are all about, they haven't changed a great deal. And when you put the text side by side, the same three questions are the same three questions. Okay, so if we take trying to design bioinspired biomimetics, this is where I'm leading. So we can, existing devices are not symbiotic, we don't have communication materials, we don't need duplex, we don't require any different biocompatibility concept apart from ensuring that there's a hermetically sealed battery that provides electrical power that can be stimulating the heart. Okay, if we then consider, instead of this heart device, we consider a device that really has to communicate with the body, then we have to really consider the idea of symbiosis and duplex systems. So just as a general background, and the devices that I'll be considering are things like, instead of batteries, fuel cells. So if we really push into a biomimetic way of delivering power, the size of a battery that's for a pacemaker needs to last for 10 years. It's a large device. You can provide more power in a device the size of your fingernail if you create inside the body a system that utilizes chemicals from the body to produce power. So it becomes an organ, a symbiotic fuel cell. One example. But to design that, one has to consider that the membrane surrounding the implanted device needs to communicate as an artificial organ does. That's in comparison to implants that degrade, like a pump or a fuel cell. And just to consider, symbiotic systems should benefit from a porous encapsulating membrane to allow transport and to avoid immune reactions. So, these are, at the end of looking at all of this, they're simple engineering things, but they're very difficult to do. Very difficult to do. So if we put that design concept into reality. This is a bioelectrode that's been designed to be implanted in the body, not as a encapsulated battery, but as a bioelectrode that is truly symbiotic with the body to take, in this case, glucose from the body to provide an enzyme reaction inside the electrode to then deliver either chemicals, as we were discussing this morning about trying to deliver therapeutic molecules based on redox reactions in the electrode, or using an anode and a cathode to combine redox reactions to create electrical power from a device that is symbiotic with the body. To achieve that, these three-dimensional electrodes were nanostructured on a basis of a polymer, a chitosan polymer, cross-linked with genopin, which is a biocompatible cross-linking polymer, mixed with carbon nanotubes. The carbon nanotubes don't escape, they provide the conduction, and the enzyme provides the ability for the electrode to convert glucose from the body fluids and create a electrical signal. And so after 6 months, there's still a problem of getting an encapsulation. There's still a little collagenous growth, a capsule around the dacron. This is the dacron that's surrounding the electrode, and there's still problems. It's not perfect. These are difficult problems to solve. The inflammation disappears, but there's still an issue about encapsulation, which, if you consider, if the design principle is to create symbiotic devices that have permeable membranes, then one has to control the encapsulation. So as an examples, so what I'd like to do, I mean, that sets the background and the stage for thinking about how to create biomimetic and the problems of creating biomimetic and biocompatible, bioinspired devices. So if we take one of those electrodes here, could turn it into a cathode, turn another electrode into an anode, just by using different enzymes, and implanting those devices, which are much smaller than a battery, into an animal. This is a Bluetooth transmitting device, which allows us to communicate with the device that's inside the animal. And after 14 days or so, 14 to 18 days, we still get a signal. We can get a device that lasts long enough, that's not encapsulated, that's still permeable enough to utilise the glucose from the body to create electrical signals. But there are still issues. It's not perfect because over time there's a degradation in the signal because overcoming the biocompatibility issues is a serious problem about bioinspiration and building inspired biomimetic devices. So, up to now, the point is, there are issues about designing bioinspired devices. Whatever nanotechnology, whatever clever nanostructural technology we might use, there are still issues that are yet to be solved about trying to make truly communicating artificial organs. Membranes are really difficult. First point. Second point is, yes, we can take a bioinspired approach, but it's not perfect. You know, we can't replace for 14 days a pacemaker that lasts for 10 years in the body. Okay, so there's still places, still directions to go, which leads us to challenges for the successful implantation, which are biocompatibility, not technical. Not technical. These are the size of the electrodes at the moment. They can be bigger, they can be smaller. The power output per volume is at the moment 16 microwatts per milliliter, far in excess of what a storage battery can do. Greater power output. But for long term, the bio-inspired clever nanotechnology really needs to be addressing the issues of biocompatibility. We still have biological problems to solve, which is which is one of the points I wanted to raise about bioinspired, biomimicry is not all about the technology. We have to choose appropriate biological components. So these are the design limitations for an engineer. These are the design limitations for anybody interested in, to my mind, anybody interested in biomimetic, bioinspired, biological engineering. So let me illustrate those challenges with some devices. And you'll notice the concept here is hybrid systems. Hybrid systems are important because we still need some technology. Clearly, we need some nanostructured technology, we need some way to do the conversion, but we do need biological components. Why? If the challenges of the implantation are the biocompatibility issues, maintaining the permeability, truly trying to make artificial organs, trying to build self-assembled membranes that really can be permeable membranes to encase implanted devices, requires biological components, which requires a new way of thinking about building implanted devices that are biocompatible, not just going to the material scientist to try and fix the material. So this is where I'd like to describe now with this kind of concept in mind. So what I've come to realise is it's just not good enough to take a traditional approach of bioengineering to make truly symbiotic systems. Okay, so self-assembly. This is what biology does. So let's try and use that in building in making the technologies. So biotechnology systems are hybrids of synthetic materials. We try and use self-assembly. If we can use self-assembly, perhaps we can fool the biological responses in the body to try and create devices we can implant. So let me give you some examples of taking that kind of approach, starting quite large and getting down into very fine levels. So one thing we've been doing, looking at the medical problem really helps to define the engineering that one needs to do and the devices that one needs to consider. So one of the aspects of the big medical problems, one of the aspects is the gut, of course, and the microbiome. Either on the skin, the microbiome everywhere, but we're looking at the gut. How do you go about using a technical approach that's not using metals of the physicist, using a self-assembled approach to try and take samples of, at various stages in the gut, of the bacterial flora that you can use for diagnosis and also for treating. So this is a little capsule that's polymer-based. There are no moving parts. It's all based on the polymer hydrogel responses to bypass the stomach, to then sample at various levels of the gut, sample bacterial load, close, and then be extracted for analysis. Okay. So the way that kind of works is that the polymer quickly absorbs material from the gut, along with bacteria and fluid. This is inside a capsule that can be opened and closed at programmable parts of the gut to sample bacteria. Okay, here's a case of using the permeability of a hydrogel, but with the desired need to completely encapsulate to protect a bacterial load that you've sampled. Okay, still the same sort of concept about biocompatibility, except it's a short-term transitory kind of thing. You know, we've looked in pigs, etc., and this is now taking a similar kind of polymer. This is the device there in the gut of a rat. The ribs the spinal cord and the rib cage. This isn't a rat. And this is now, instead of sampling, this is taking the same polymeric approach to an indwelling device that can deliver therapeutic bacteria at different parts of the gut, knowing what's there and then what can be delivered. Okay, that's an approach not MEMS, not micro-MEMS, not physics-based, but it's based on understanding polymers and polymeric materials. Still related to trying to create symbiotic systems. Okay, let me give you another example. As I said, some examples of how one takes these approaches to think about devices. I can come back to details of questions later, but I'll just skip through these a little quickly. This is a rotating hemisphere which is designed to mimic an acinus, like this. The reason for doing that is that one can make organoids quite easily, spheroids, organoids, but you can't get to the inside. You can't get the secretions. So if we're taking the principle of symbiosis, but not as in the gut, not of sampling and then quick passage. If we're taking the concept of trying to create a diagnostic and a therapeutic organ where the inside of the acinus, the inside of the secretions are important, you can think of many examples. You know, islets of Langerhans is a big important example. Organoids of the islets of Langerhans, it's very difficult to get the secretions out, only through diffusion. But if a system like this exists, where there's a nanostructured basement membrane, illustrated in red, the epithelial cells are growing on the inside, illustrated there. The stromal cells are on the back to keep to basically mimic the external organ. And then small volume secretions, nanoliter secretions. So does it work? Well, this is an example of B and D are the positive control, and this is testosterone-stimulated secretion of PSA from a prostate cell line. Negative controls are not stimulated, and from a kidney cell line of the epithelial cells growing in these little acina lookalikes. So the point is, the principles that I'm talking about of biocompatibility, trying to self-assemble and consider the issues of permeable membranes to support, in this case, an artificial organ, as in a diagnostic system. And as an example for a diagnostic, we're using this to seed patient cells from the urine, for example, from first-pass urine, to put potentially cancerous cells into an existing epithelial bilayer and change the nature of the secretions. And we can measure that. Okay, but then this also has potential for, if you have the right sort of cells, you can create a closed-loop insulin secreting system. Another example. So let me just delve a little more deeply into that kind of artificial organ type approach. Instead of making tubes of plastic, instead of making tubes and metals and things, trying to consider a self-assembled approach to overcome some of the potential issues regarding biocompatibility. So these are ductal structures that are made, the grey illustrates a basement membrane, similar to the acinus lookalike, but these have been grown, these are now epithelial cells growing in the tube. So taking slices at the top and the middle of the bottom of the tube, these are horizontal slices from the bottom, the middle and the top. And these are stained, Herc-stained and Phalloiden-stained epithelial cells. The cells grow into monolayers in the tube, and they create the equivalent of a duct. So there's a little toolbox. So there's a toolbox of ducts that you can combine with acinus to then start to rebuild, self-assemble an organ. Not carve it out with microfluidics, but self-assemble it. And just these are different cells growing on the polyelectrolyte substrates, but those cells grow into monolayers. They develop junctions, epithelial junctions. This is E-cadherin for epithelial cells. And so the cells actually in a tube can actually form quite nice structures. So you can kind of build these kind of cells. Okay, another example. Let me move on to yeah, these are 150 micrometers or so. Yeah, yeah. It can be programmed bigger or smaller, but these ones were 150. Yeah, so let me illustrate the concepts with another example before I get more deeply into the nanostructural molecular biology. This is an example of quite old work. I added this after discussion, but this is on a silicon substrate of pericytes that are contracting. The point about saying this is that depending on the nature of the cell type, you can change the function of the end symbiotic organ that you can consider to build. By starting with a nanostructured substrate and then self-assembling cells onto that, you can make, in this case, contractile cells that respond to vasoactive peptides, control peptide washout. You can control the function of a cell that is assembled onto a nanostructured substrate. So the point, why do that? Why do that? Because there's an interesting and useful diagnostic process about investigating the contraction of pericytes or investigating, in fact, ion transport in astrocytes, which I won't discuss, but that's another aspect. So if we know that pericytes can contract and dilate, in this case, the drug was to relax. So the retina is a nice place to look because you can see real blood vessels. And so in a diabetic rat model, the vessels dilate. And so by measuring a threshold of which there's dilation or not, there's an indication that there's a pericyte damage. So in terms of looking at nanostructured biocompatible devices, this kind of diagnostic system, I won't discuss too much of that unless you really want to. It's just to say if you model the economics, the health economics, measuring early stress tests really saves a lot of money and saves a lot of site years and can be of benefit to the patient. The key point for the technology is that by creating devices that are built and self-assembled onto nanostructured substrates, you can actually create biocompatible symbiotic systems. Okay, so let me move on just with another example. And this, instead of epithelial cells, we're moving to endothelial cells on the basis that soluble VE cadherin. A medical problem exists. I can go into details if necessary, but a medical problem exists where a stent that's inserted into an artery, coronary artery, or any artery, causes endothelial damage. After 6 months, there's restenosis, and there's problems with the way that the stent reacts to the body. You can either have a stent with paclitaxel or drugs that are released to reduce the restenosis, but after the drugs are eluted completely out of the polymers or the stent, then the re-endothelialization, the restenosis occurs. That's taking a material and then trying to fix the problem after the biocompatibility issues exist. If we take the problem the other way and try and build a material that can ensure that there's no soluble VE cadherin, in other words, the endothelial damage does not exist, then we can make a better implanted vascular device to avoid the endothelial damage and hence avoid any restenosis problems. So it's like taking the concepts of symbiotic bioengineering and trying to build systems that can avoid the issues. Why soluble VE cadherin? Because endothelial cells are stuck together with VE cadherin. When any event causes a breakdown of the endothelial cells, the breakdown of the monolayer, VE cadherin is cleaved. There's a phosphorylation-dependent cleavage, and the extracellular domain, the soluble VE cadherin, is available in the bloodstream for measurement. But she's looking at vascular endothelial physiology. The difficulty is that if we don't have a maintenance of VE cadherin, then there's a breakdown. There's soluble VE cadherin as a biomarker for cancer or for endothelial breakdown, and we have problems. The issues here are the measurement system is not an endothelial system. It's a biomimetic membrane that's self-assembled to measure the adsorption of SV cadherin. So we can use the adsorption onto a biomimetic membrane by measuring the not so much the conduction properties, but the dielectric properties of the biomimetic membrane as a diagnostic. Turning that around, we can self-assemble a membrane such that instead of adsorbed VE cadherin, we can maintain endothelial cells in an environment where they don't break down. So, point is, looking at the biocompatibility issues in doing the design for implantable symbiotic systems means taking a self-assembly approach to ensure that the natural physiology is maintained, rather than trying to take a material and treat that material with drugs to avoid the biocompatibility issues. Okay, enough of the examples. Let me dive into some of the more details of how I'm going about this in terms of design and nanostructured in the lab. And so the nanostructured basis, the scaffolding, is built around, at this stage, of polyelectrolyte layer by layer chemistry. And this is an example of putting a lipid bilayer, adding to a nanostructured scaffold, and to this bilayer adding various engineered ion channels to create transporting capsules. So as a general principle, that ion transporting vesicle provides a signal that you would see, a patch clamp signal, for example, that you see from the ion transporting proteins that are in the membrane that can be controlled on or off, in this case off, by inhibiting drug. You know, just to put detail, this is a bisgramycidin engineered protein that was inhibited by benzalkonium chloride. But the principle exists for any particular ion channel, whether it's, in this case, engineered, or whether it's produced or cloned from any system. So how does one use that? So one can create this as a model if, instead of a vesicle, if there's a flat lipid structure. And if you remember some of the previous slides, the examples had flat scaffolding structures, some had curved, hemispherical. The principle, if you take a nanostructured scaffold, add to it a biomimetic self-assembled lipid bilayer, build up a biomimetic layer, then putting ion transporting proteins helps to start the process of thinking to overcome the biocompatibility issues by self-assembling with hybrid components, chemical plus biological, to then start to think of maintaining a transporting membrane around an implanted device. Okay, so as a sensing system, by modelling the signal, just with, again, we're talking about duplex, I mean, applying the electrical engineering concepts to signals like this using a stochastic algorithm. By changing the nature of the ion channel, you can change the principle of this approach, hybrid system, by changing the biological component, you can change the specifics of whether you create a system that's going to be secreting. So if we put secreting the ion channel machinery and the cellular system for secretion, then you can use the principle to create a secreting system or as a sensing system. The point is that that's the approach of a symbiotic system is a slightly, to my mind, a different way to consider. Yeah, so we take that approach, and here is in fact, it's the NHA transport protein in a system where there's 6 membranes. Okay, so this is now taking the approach of building a nanostructured scaffold membrane with biological components to do something in a sense. So with no protein, there's no voltage output. With sodium chloride as a trigger, we can generate 20 millivolts or so from a system like that. Yeah, not really implantable, except if you turn it into 3 dimensions. So if you make vesicles and add in a cell-free system the correct protein to the membrane, then we've got a system that can, instead of a dozen or so vesicles, we make this kind of system, which looks small, but it's a AAA battery size. It's not a storage battery. Now we've turned the principle of a nanostructured scaffold, adding biological components to a system that's 3 dimensions that transports with transporting proteins. Now we're extracting the voltage that's generated by the ion gradients and generating 4 milliwatts for a mil. And you know, a Toyota Prius generates 64 watts per kilogram. This generates 4 watts per kilogram using protein, lipids, salt, and a plastic container. What's really useful in engineering systems like this, you know, the principle is there, but as an engineer, to make the systems better, I need to understand exactly on 4 nanometer membrane what the transport properties are, the conduction properties, what the structure of the protein is. This is an example of using a neutron experiment, neutron reflectometry in this case, at the Institut Louis Langevin at Grenoble. And this is an example of a viroporin that was added to the lipid bilayer, self-assembled, all on a flat substrate. Self-assembled using all of the promoters in the fluids above the block of the neutrons. So this is using biological self-assembly to build a system that is nanostructured that transports. So take that concept and just do a mind experiment. Instead of a neutron block, self-assembling this on top of a stent or on top of a medically implanted device gives the ability to create what will start out to be a better chance of being biocompatible than taking a material, a hydrogel, and trying to make size exclusion and adding drugs to keep the biocompatibility. And here's an example, just interpreting the signals from the neutron reflectometry. One can measure where the bilayer is in green. One can measure where the protein, in this case the P7 porin, where the his tag is. And this conical structure was calculated from the measurements we made neutron scattering. This is the crystallography example, overlaid on top of what we can do real-time, nanostructural. This is nanostructural characterization at the same time as one can do nanostructural transport phenomena. So as a design tool, it's really useful to understand how the biological self-assembly is going. Yes, good point. I will finish soon. So these are examples to illustrate the principles of taking a symbiotic approach to biocompatibility, some examples of taking this approach into engineering hybrid systems that are containing biological components. So let me just, this is kind of sharing thoughts. What's the future? How do we interface with people? The last thing I really want to talk about, and that is these three-dimensional systems, just to summarize. These three-dimensional systems, which could include ASNI, they could be neuromorphic architectures, they could be artificial organs. The scope of using the principle of hybrid nanostructured membrane with biological self-assembly is the principle that I think is going to help to overcome truly symbiotic, the ability to make truly symbiotic systems, which can be interfaced. So with that, thank you for your attention, and I'll